We're looking at differentiation techniques. So this page here, the first page, if you do have this as a PDF or you do have it as a printed out document, this is just going to be with the notes of the main ways of differentiating functions. So that's looking at polynomials, using product rule, chain rule, quotient rule, all the good stuff. Then the next page, we have a few examples. The side on the left is what I'll be working through, and the right hand side's the your turns, just to make sure that you've got those skills down pat. The next page will be looking at differentiating functions and finding when gradients equal certain things, or finding the gradient. So let's have a go at this there, differentiation techniques. Now, if you do want to access this, you can go on the OneNote. It's under test 5 and then 1 point, and then I'm going to start adding more things to this. I think there'll be about 4 videos is my estimate of just an overview of everything. All right, let's get cracking. So first thing, differentiation is either express, if you've got function f of x, we express it as f dash x, or y becomes, dy by dx. We can also be a bit lazy and go y dash as well, y prime. So there's 3 ways of basically writing out how to differentiate. Okay, now what is differentiating doing? It's finding the gradient function, okay, of a function. So it finds the gradient function. Now it also can help us find rates of change and lots of good stuff, but this is sort of the main stuff we've got to know. Let's look at our main kinds. We've got the polynomial. Okay, so what that looks like is if you've got a function like this, y is equal to ax to the n, then if you want to differentiate that, you bring that n down and take 1 off the power. That's our main bread and butter rule there, that polynomial differentiation. And remember, we showed that using first principles. Okay, the next one, we could go into, just trying to have a look here, the product rule straight up. We could, I think I'm going to write chain rule first. Okay. Now, chain rule is simply a way of simplifying a problem by breaking it up and using something known as a dummy variable typically. We typically use the letter u to represent that. So you might bring in a letter u, which is a dummy variable, and it helps simplify some of our problems there. Okay, then chain rule can generalize a lot of things. What chain rule can now do, if you apply it, is it can make the power rule. Now what that one is if you've got y is equal to some function to the power of n, we can use chain rule to help us show that you bring the n down, you keep the function f of x the same, you take 1 off the power, then you times by the gradient of that function that was inside the bracket. Okay, so that's what's amazing about chain rule, is that you can use chain rule to generalize and find some pretty nice patterns. So that's power rule there. Now let's go on to product rule. So product rule is a bit more powerful. If you've got 2 functions that have like an x and they're multiplied together, then you can use this one. So you might have something like this, u dot v, where u is a function and v is a different function. If you want to differentiate that, u dash v plus v dash u. Okay, and you're multiplying them together. So that's a really handy one. Okay, we've also got the quotient rule. Okay, now this is quite similar to the product rule, but you've got a function u on the numerator and a function v on the denominator, so hence quotient. Product is because 2 functions are being times together. Quotient, 2 functions are being divided together. So that looks like this. Now, how to remember this one, I usually do the bottom first, that function on the bottom gets squared, v squared, and stays the same, then how to remember this is that you get the u and you differentiate that one first, okay? So whatever's on the top, you differentiate first, then times by the bottom, and then quotient rule, there's a take here, and that's why that bit's important. There's not that symmetry that the product rule has. Then you flip it, v dash times by u. Now, people write this in slightly different ways. This is the way I like to do it. I like to put the gradient function as the coefficient typically. All right, let's move on. Let's look at, so we've done the quotient rule, power rule, product rule. How about we look at some natural exponentials? That's going to be confusing green on green, so I'll go to purple. The natural exponential, okay? Now that one there, you've got y is equal to e to the power of f to the x, where e is the exponential function, the natural exponential function. Remember, e is equal to 2.718. So let's differentiate that. What happens is you can just bring that gradient function down and keep that same e f to the x. And we also may remember that amazing fact that if we are just differentiating the exponential function, it becomes the exponential function. And we did that with the visualizing of the graph. All right, now let's move on to the next one. Now we can go green. Let's look at logarithms, and I should say natural logarithms. Okay, so if we want to differentiate these, this is log base e f of x, and this one's amazing as well. It seems scary to differentiate logarithms, but they're actually not too bad. The f of x goes to the bottom, and on the numerator is the gradient function. Now remember that this could also be expressed as ln f of x, okay? All right, now another thing we consider is also differentiating by first principles and also just the average rate of change. We look at rate of change in another video a little bit later on where we're looking at applications of things, but differentiating by first principles is definitely one to know. So first principles. Now, obviously this way is a far more long-winded way, but it's using limits to help show the gradient functions of any function you want to use. You can plug in a polynomial, a cube, which like a cubic, a quartic, whatever, but it also does sine, cosine, logarithms, exponential functions. You can throw lots of things at this, and if you know your calculus, you can help show what the gradient function is for lots of different functions. And that's why it's called differentiating by first principles. Now, what we have here is you have your limit as h approaches 0, and then we've got f of x plus h take f of x on h. And we can remember this if we remember trying to differentiate our quadratic. We might have something like this. This is exaggerated. This is our x. This is our x plus h. And this is our function when we're plugging in just x. And this is our function when we're plugging in x plus h. And what we're doing is we're finding the gradient here, rise over run, okay? Now the rise is going to be f of x, f of x plus h minus f of x, and then the run is simply just going to be h because we're adding on h there, and the limit there is saying, hey, my h is going to go to 0. So if you picture where we can call this point P and Q, right? Point Q is going to get incredibly close, and this is what the limiting chord process was just bringing that point Q, bring as close as you can to P. Now with that in mind, we're going to go on to the next part, which is just differentiating some functions. So here we go. All right, so let's differentiate some functions of the stuff that we learned before. Okay, now I'll go on green. This one here, f dash x, this is a polynomial, so it becomes 6x take 4. The next one, you want to rewrite, I was meant to write that as a square root symbol, pretend it was. Okay, then we can differentiate, and that'll be negative 6 x to negative 3, and then take x to negative half. Now we can express this as positive indices, which I'll write up here, negative 6 on x cubed, take 1 on the square root of x. It is good practice to be able to swap them around if we have to plug and find a gradient. For instance, what happens when x is 4? You can see that top rule is going to be so much easier. You can plug the 4 in, you can see 1 on the square root of 4 is going to be 1 and 2, so it's really nice. Okay, this one here, C, is going to be using that chain rule. So dy on dx is equal to dy by du, which is going to be 6u, times by du by dx, which is going to be 4. That's going to be 24u, and then we plug in that u value, which becomes 24 4x plus 2. Then you can expand that if you so wish as well. Okay, now remember that's our chain rule. Let's move on to the next one. This is a power rule. So you've got 3 comes down to the front, take 1 off the power, and then differentiate the insides like that. Then you can rewrite that as 12x lots of 2x squared minus 3, the power of 2. The next one we can see we've got our product rule here where this is function u, this is function v. So let's differentiate that. I'll zoom in on this one. Okay, so this one's going to become 2 minus, oh sorry, this is u dash, right? Yep, happy with that. That's u dash, we times it by v. And then we add, and this one's going to be v dash, so this is 3 lots of u, which is 2x minus x squared. Now with these, you can expand them and try to simplify them. So if we do that, it's going to become 6x plus 2, take 6x squared, take 2x, plus 6x, take 3x squared. Let's get those x squareds at the front. So we've got negative 6x squared, take 3x squared, which is negative 9x squared. We've got 6x plus 6x, which is 12x, then minus 2x, which is 10x, and then we've got positive 2 just by itself. So we can do it like that as well. Okay, let's look at f. This is going to be a quotient rule with u on the top, v on the bottom. So let's differentiate that. Okay, we square the bottom, and I'm just going to leave it as a squared. And then we go u dash, so that's going to be 5, v, 2x plus 1, take, and then we're going to go v dash, which is 2, lots of u, 5x take 4. You can clean that top up. So we've got a 10x minus 10x, they cancel. Then you've got a 5, and then you minus a negative 8. So I think that's going to be 13 on 2x plus 1 all squared. I hope that's the case. I just don't have much space there, so that's good. Okay, now g, we've got an exponential function here. So to find this, we're going to keep that 2 at the front, and then we're going to bring the gradient of the power down as a coefficient. So it's going to be 2x plus 3, e, and then we just keep that function as is. So we leave it there. And we can, if we want, we can expand this as well. Well, that is definitely not 6. So 4x plus 6, lots of ex squared plus 3x minus 1. Okay. Now this next one, h, we can see it's a natural logarithm. So we know this is y is equal to 3 times by, and then what happens here, the function f of x, which is here, is going to the denominator, and then the numerator is the gradient function of that, which is simply 10x, and we can times that by 3. Remember, if you get confused with the fractions, which I know we do sometimes, it's 3 over 1, so times tops times bottoms. So you've got 30x over 5x squared plus 1. Okay, what I'd like you to do now is basically pause the video, have a crack at these, and then when you're ready to go, press play. All right, so let's see what we get. Next one, rewrite. And we can express that as a like that. Let's move on to the next one. So we can see this is a chain rule. So let's go dy by du. times by du by dx. So we've got 9 on 4, let's sub in that u, 3x take 1 all squared. Next one, dy by dx is equal to, this is a power one, take 1 off the power, and then times by the gradient function. And what we can do is bring that 4 at the front. So it's going to be negative 60x squared plus 4. And you don't have to do that. You can just keep that 4 at the front if you want. Okay, there we go. Next one. Now, there's two ways of doing this. Let's use product rule just to practice it. So it's going to be 2x u dash times x plus 3 plus, and then 1, that's v dash times x squared. And we get our answer of 2x squared plus 6x plus x squared, which is 3x squared plus 6x. Now, why I like this one is you can also expand it, and it becomes x cubed plus 3x squared, and you can differentiate that, 3x squared plus 6x. Now, do you see sometimes they may give you a question where, yeah, you can use product rule if you like, but also if you're pretty handy with your algebra, you can just expand and then differentiate normally. This one, D, are we up to D? I feel like we've done A, B, C, C, D, D. Well, that doesn't make any sense. So this should be E, I guess. We know what we're doing, right? Who wrote these? Okay, so this is U and this is V. Let's differentiate. Dash, square the bottom. Okay, then we differentiate the top first. So that's going to be 6x times by the v, 2x plus 3. Remember, we minus for a product rule, and I keep extending that line like I always screw up. And then v dash is 2x, lots of 3x squared plus 4. We can clean up that top if we like, so it might become 12x squared plus 18x minus 6x squared, take 8, all on the same stuff. And at the top, the numerator is going to become 6x squared plus 18x minus 8 on the same. You can expand that bottom bracket as well if you like. Moving on to E, which is probably F or maybe G, who knows. Let's differentiate. We differentiate and bring down as a coefficient and then keep the power the same. And the last one's logarithm. This is, I just had a bit of fun with this one. Apologies for making you do this. And on the top, we're going to differentiate. So you've got this. Okay, then you can times everything by 2 if you wish. There we go. All right, now what we're going to do is going to move on to the next section here. Finding the gradient when, and we're just going to be working through these problems now. So this is finding the gradient function. And when we're finding the gradient function, the gradient function actually helps us find the gradient at a certain point, in particular x. So if we want to differentiate this, which we know how to do, right, it's going to be 3x squared minus 4x. We can now evaluate, hey, I've got my graph here. Listen, this is going to look like a cubic, right? So I can draw this in, positive cubic, looks something like this. What's going to be the gradient when x is negative 3? I'm not sure where x is negative 3. It could be around here. I'm not sure yet, but we can plug in that negative 3 and figure out what the gradient is. Is it like this, 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 wherever the tangent lies? So let's plug it in. And 3 times 9 is 27. Take negative, so it's 12, so 39. So the gradient is very steep positive at negative 3. So I'd say most likely it's probably going to be like that, or it could be over here like this. We're not sure what part of it, but yeah, more or less that's what we got. Okay, let's differentiate the next one and find the gradient. Now, I really like function notation because we can sub in values. So that's more or less easy enough to do. E to the x is just simply e. And it might have been at times originally, but let's just say it's a take just for simplicity's sake. Oh, let's make it a times. We should practice these. So product rule, so let's pretend this is a times. Okay, sorry about that. Okay, and differentiate the first, which is still e to the x and then x squared. And then plus, and then you go 2x times by e to the x. Okay, now let's sub in -3. So e to the -3, then this is going to become 9 plus -6 e to the -3. Okay, and what we can do is, like terms, e to the -3 is the same as the e to the -3, so I can go say I have 9 e to the 3 take 6 e to the 3, so therefore I've got 3 e to the 3, -3, and I can rewrite that as this. Now this is called an exact gradient. I could put that in my calculator and find it to 2 decimal places. Let's move on to the next one. Find the coordinates and the gradient is 6. Now this is a bit of a classic question. You firstly want to differentiate. 3 times a third is simply 1, so x squared minus 4x minus 6. Then you want to find when the gradient is 6. So this is saying f dash x is equal to 6. Okay, so wherever we see the f dash x, the gradient, I replace it with 6, like this. Rearrange to solve. If we see a quadratic, we know null factor law is the way we're going to solve this. Usually it's a factorize. Sometimes it might not be. This is a nice, this is a nice monic, so that's good. And then we can find that x is going to be 6 and -2. Now here's our common error. We forget it's a coordinate, so we have to sub this back into not our f dash x, which is our gradient function. So remember, you can write this in a test as well. This function is only for gradients, right? This is for coords. So we want to plug into the original f function. Now I love function notation because I can write this, f of 6 and f of -2, and then you sub in and you find the values. Okay, now this is, I didn't think ahead here, and 6 is going to be absolutely an absolute nightmare here. Do I have my class pad here? Ugh. Anyway, you know what to do. We'll just plug it in. I'm just going to go f is -2 because I'm lazy. Okay, sorry. So third, -2 cubed, take 2, -2 squared, take 6, lots of -2, plus 1. What do we get? We've got -3 times by -8, take 2 times by 4, plus 12, plus 1. And even this is sort of gross because we've got this fraction here. Take 8 plus 12 plus 1. And we can go, that's going to be 4, so 5. Okay, and then we better do it right. -8 on 3, and this is going to be plus 15 on 3. Did I do that right? Yes, times by 3 and 3, and then this is going to be 7 on 3. So therefore we can write out the coordinates, and I should really double check my coordinates before I make myself do this just live. -2 7/3. Okay, now what I'd like you to do is on the right hand side, you've got these 2 examples. I'd like you to have a go at these. And so pause the video, press play when you're ready to go. Okay, so let's have a look at these. Y dash is going to be 6x, and then, hang on, before we do that, common error, rookie mistake. Let's bring that up to a numerator, then we differentiate. Zoom in a bit and give myself a bit more space. 6x, and then take 4x and -3. Let's sub in x is -2 into this. Okay. And this is going to be -2, and I'm going to rewrite this as positive cubed. So I've got -12 take, and then I've got, that's going to become a positive because it's going to be 4 on -8. Okay, right. So this is going to be -12 plus a half, so it's -11.5. Okay, -11.5. Let's move on to the next one. F dash x is equal to, and this one here is going to be, you keep that there, and then you put the 2x on the top. Then we sub in -2, -2 on 4, take 4, and we can say that it's undefined. I can't believe I chose a value here that didn't really work. So that means that the function can't exist here, and that's quite embarrassing because you can't have ln of 0. So this is why you should do examples first. So what we're going to do is we're going to practice doing x is equal to -1. No, that's not going to work. Let's go x is -2. 3. That should work. Okay, let's see that. So let's plug in and let's just practice doing this just so we actually get an answer. -6 on, it's going to be 9 minus 4, -6 on 5. There we go, there's our gradient. Okay, let's have we got this last one. Find the coordinates where the gradient is -3 for this function here. So let's differentiate. Plug in when f dash is -3, rearrange to solve, and that's going to be +3, so that take 1, I think. Okay. Did I screw that one up? Let me just double check. Oh no, that's annoying. I'm gonna have to make it 0. Oh, I mean, we could solve for this. We could use turning point form. It's brutal. This is why you should test your examples first. I thought I had this right, so let's have a look. 7x. I wanted to make it originally 2x squared take 7x take 4, so I didn't extrapolate that. So we're going to change this to a gradient of 0, okay, and that's going to make life way, way easier, okay? So let's do that. So I must not have gone one step ahead, okay? Now we can see that this is a non-monic, sorry. So when is AC equal to -8? Okay, now let's think of two numbers that times together to make, -8 and add together to make -7, okay? Now we can see that those numbers are going to be, what, -8 and +1? I think that works. So let's break that up. Factorize in pairs. And then factorize again. Then solve. Okay, and then we can find those coordinates by subbing in. Okay, and we can just do that using a calculator. Okay, so hopefully that all made sense. You can just double check those coordinates because I haven't done all these examples. I've sort of rushed through this, to be honest. I hope this all made sense. We can do a differentiating by first principles in another video. I just feel like this video is quite long, but it is an overview of most of the differential techniques. In the next video, we're going to be looking at tangents and norms. I will do a video later on differentiating by first principles. Then we're going to look at the key features of graphs. Then in the fourth video, I'll be looking at the applications, so rates of change, optimization, and all that good stuff. Okay, thank you. I hope this video was useful. Thanks for your time.